Okay, so in this video, we will consider the following family of linear systems. We've already written the system in its augmented matrix form, and as always, k is our parameter, x, y, and z are the variables, and as we let k vary over all real numbers, we will get an infinite number of linear systems, and the question is, for which values of k will the system have no solution, a unique solution, or an infinite number of solutions? Let us row reduce and see what pops up. We already have a leading 1 in the leftmost column in the top row, so we can use it to kill these other two entries. So we'll do row 2 minus row 1, and we'll do row 3 minus k plus 1 times row 1. Be careful to negate the entire k plus 1. Let's see what comes out. We can recopy the first row as we're not changing it. First row operation, quite simple, row 2 minus row 1, so 1 minus 1 is 0. K plus 3 minus 3 is k. K plus 2 minus k is 2. K minus 2 minus 0. K minus 2. And that's it. The second row operation is a bit more interesting. Row 3 minus k plus 1 times row 1, so k plus 1 minus k plus 1 times 1, while k plus 1 minus itself is 0. This will do on the side, so 2k plus 3, let me do it here, 2k plus 3 minus k plus 1 times the entry in row 1, which is 3. So what do we get here? We get 2k plus 3 minus 3k minus 3. 3 minus 3 cancels. 2k minus 3k is negative k. Second entry, 2k squared plus k minus 3. Minus k plus 1 times the entry in row 1, which is k. So what do we have? 2k squared plus k minus 3. K times k squared minus k squared. K times 1k minus k. 2k squared minus k squared is k squared. K minus k is 0. And we're left with a negative 3. So k squared minus 3. Finally, this is quite simple. 3 minus 0 times k plus 1 is 3 minus 0, which is simply 3. Now if you notice, we have our first leading 1. We've killed the entries below. So we ignore the top row, and we go on the hunt for our second leading 1. It's not going to be here. Here, both entries are k. And here be careful not to multiply row 2 by 1 over k, as k could be 0. K is allowed to range over all real values. And if k is 0, you can't do 1 over 0. So all you have to do here is be happy with a potential leading 1. So leave k as it is, as a potential leading 1, and now kill the entry below it. This is quite simple. We'll do row 3 plus row 2. So we can recopy the first two rows. K squared minus 3 plus 2, minus 3 plus 2 is minus 1, k squared minus 1, which does factor as k minus 1 times k plus 1, of course. 3 plus k minus 2, well, gives us k plus 1. And this is our other potential leading 1. We've reached the bottom row, so we're done with our reduction at this point. As always, there are two possibilities. all the variables are leading, or not, and we start with all the variables being leading. Well, the only way for this to happen is with k not being 0, not being 1 or negative 1. If k is anything but 0, negative 1, or 1, both of these entries are not 0, they can be turned into leading ones, and so x, y, and z are all leading. And if all variables are leading, this implies, of course, a unique solution. And that's it. And now we're down to, as always, our three in this case. I mean, there could be 5 exceptional values, but we're down with checking the exceptional values. And here we have no choice but to check them one at a time. So k equals 0. We'll get 1, 3, 0, 0, 0, 0, 2, negative 2, 0, 0. If you plug in here k equals 0, you get negative 1 times 1, which is negative 1, 1. So let's see here. Again, the matrix is not fully reduced. We have the leading one for x. We've killed everything below. And here we're looking for possibly a second leading one. Well, let's be crafty here. If you multiply row 2 by 1/2, this will become, and I'll be a little messy here, but this will become a 1 and a negative 1. And if you now do row 3 plus row 2, negative 1 plus 1 is 0. 1 plus negative 1 is 0. And so you see that x is leading, z is leading. The bottom row is a row of all zeros, which says 0x plus 0y plus 0z. For any value of x, y, z, the result is 0, equaling 0. The system is consistent. X and z are free, but y is leading. I'm sorry. X and z are leading, as they both have a leading 1, but y does not, so y is free. The system is consistent, y being free, and plus y will become a parameter, which will give us an infinite number of solutions. That takes care of k equals 0. Let us now check k equals 1, or k equals negative 1. So we'll get 1, 3, negative 1, 0, 0, negative 1, 2, negative 1, negative 2, negative 3, 0, 0, negative 1 plus 1 is 0, with a row of 0 coefficients. Negative 1 plus 1 is 0. If you notice, x is leading. We could turn this negative 1 into a 1, so y is also leading. We have a row of zeros. The system is consistent, but here z is free. As z is free, and the system is consistent, z will become a parameter which will give us, once again, infinitely many solutions. We're down to our last exceptional value. What happens to the system when k equals 1? The first row will be 1, 3, 1, 0. The second row will be 0, 1, 2, 1 minus 2, negative 1. And the third row, 0, 0, 1 minus 1 is 0, 1 plus 1 is 2. So we'll get 0, 0, 0, 2. And this is obviously inconsistent. The bottom row implies that 0x plus 0y plus 0z, which is always 0, equals 2. 0 is not 2. The system is therefore inconsistent, so there is no solution. And now we're done. We can finally write a proper conclusion. when the system has no solution, a unique solution, or infinitely many solutions. The system has a unique solution for any real value of k except for the three exceptional values, which are 0, -1, and 1. And this is the case because for any value of k other than these three, we have three leading ones, three variables, all variables are leading, therefore a unique solution. The system has an infinite number of solutions when k equals 0 and -1. And the system has no solution when k equals 1. And this is our conclusion. So the system has no solution only once when k equals 1. The system has an infinite number of solutions twice when k is -1 or 0. And for every other value of k, the system has a unique solution. And we're done.